Okay, good morning all. Right. So today, morning session or the early session we'll do data structures. So then we'll move on to the data management as well. Okay. Right. So last time we finished discussing queues. I have not uploaded the queues note, I think, because I have to do a little bit of change. I will be uploading maybe tomorrow morning. Okay. Right. Sorry for that. So today we start our next data structure. That is trees. Okay, trees. So trees is a big topic. Let me check whether the note is available. Yeah, so before moving to the tree data structure, we'll quickly look at recursion, because we need recursion uh, in order to understand few algorithms used in trees data structure. Okay, so we'll first look at the recursion. Then we'll move on to hash table and analysis of algorithms. Those are very small topics. So then only we'll move on to the trees. Okay, right, recursion. So what is mean by recursion? So recursion is basically, we have done this in semester one also when we do the programming. That is a method calling itself, right? If a method can call itself, we call it recursion. So let's do it in a practical way. I will be using IntelliJ. Right, so let's create a Java class. We'll see recursion basics. So we'll rename it later. Right. So let's say I have a method, say void, say foo. Let's have a out. Let's say foo. Say this is my main method, PSVM. Right. So I can call the foo method. That is normal thing. Okay. Because I'm calling it from the static context, I have to make it static anyway. That is object-oriented programming, right? So you know that static, right? So that is the normal thing. The method calls, and of course the foo method can call another method, and but so on. So that is what is uh, the normal thing. But recursion means if a method calls itself, okay, so if a method calls itself, so then when I call the foo method, it prints it, and again it call itself. So that means it keep on calling itself. So therefore, so this is a recursion, but this is not a very useful recursion because it's a never ending recursion. So if I run it, it will keep calling foo, and it will be running forever. And after sometimes the JVM will detect that this is not going to stop, and it will break it. Okay, so that is the idea behind, you can see. So it run for many times, and then it has stopped it because it's never ending. Right. So we can use this concept to solve some problems in a smart manner. And almost all the topics we cover later from today, that trees, graphs, then sorting algorithms, searching algorithms, we can use this concept of recursion for our advantage. So the idea is the concept of divide and conquer. So rather than building the solving the bigger problem, we try to solve a smaller problem recursively, thereby the bigger problem must be solved. So that is the idea. Okay, so rather than solving the bigger problem, we recursively solve a smaller problem, and effectively, by recursively solving the smaller problem, the bigger problem must be solved. So that is the idea. Okay, so not all the problems can be solved like that, but there are some problems which are naturally fit into this particular approach, and we can solve that in a very elegant or smart manner. Okay, that is the idea. But if you just call it, it is a never-ending recursion. So that is not practically useful. So therefore, always when you call a method recursively, there must be a way out condition. So that means after calling the same function few times until your problem is solved, it must get out of the recursion, right? So that is super important. Otherwise, that is a useless recursion, right? Because it never ends. So for example, we can use a parameter for that, or else you can use something inside the method. For example, if I have, or you actually the inside method is not going to work, something global variable, right? Something like a global variable, or you can use a parameter, right? For example, if you want to use a global variable, right? So remember, this is a static method because I'm calling from my main method, but it is not a must. If you are calling it from another class and creating object, okay. But because this is a static method, okay, maybe I can make it a non-static method and create a object and call it as well. So there is another possibility. Okay, right. So let's do like that. So let's so this is my I will take the test class to the other side. Okay, so let's say recursion basics test. Okay, so that here we will have the main method, so that we can use the object orientation as well. So recursion basics equal new recursion basics. Right, now I will call the foo method. Okay, so anyway, still it's a never ending loop, but now I can remove this. Right, so now still this is never ending recursion. So let's run it and see. Right, it's a never ending recursion, and after sometimes it got break up. Okay, right. So how to solve this problem? There are two ways. One approach is you can have, again, instance variable will not work, because then, yeah, instance variable will work. Okay, right. Yeah. So say int x, we initialize it to something like 1. We'll say, let's assume after each iteration, we increment this. Okay, we increment this, say x plus plus. So then still, of course, it will be keep on calling, but what we can do is now we can introduce a condition. So you have to understand what is this idea behind recursion is, okay? How to build solution using recursion. It's not just learning that recursion is calling a method itself, okay? Right. For example, I can check whether if x is less than, say, 10, or less than or equal to 10, I will call the recursively call itself. Okay, I will recursively call itself. Otherwise, of course, we don't call it. Right? We don't call it itself. So then what will happen? Every time before calling the method itself, we increment x by 1. And after some times, what will happen? X will become 10. So when X become 10, oh, sorry, X become 11, it is not going to call itself again. Okay. So therefore, now let's see what happens. Because we are using just one object. So we are not creating objects again and again. So therefore, this won't be initialized again only once when you create the object. So therefore, we are using the same variable. Okay. Right. Now let's see what happens. Oh, why is that? What is the reason for that? We create only one object. We keep increasing X. Anyone can see why? Because we increment it later. So therefore, it never get a chance to increment it, right? So therefore, we have to increment it before that. I don't know whether you got it. Yeah. So because it never got incremented. Right. So now let's see. Right. Now you can see that it called 5 times, or sorry, 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then it finished because it no longer call itself. Right? It no longer call itself because it doesn't come to the if condition. So therefore, it get out of the if condition. So now it's very important to understand this because this is not just understanding what is recursion. So you must be able to solve problem using recursion later. So here what happens is we call the foo method. So then foo method calls itself. Of course, it calls itself, but we just show it in a different way. This is also foo. This is also foo. Let's make it 5 rather than 10. Because otherwise I have to draw a lot of things. So now it will call itself 5 times. Right? 5 times. So this is first, second, third. Okay, let's say 4 times. Okay. So after fourth attempt, so let's make it 4, okay, not 5. We can even make it 3 also, just to make it very simple, short number of times. Right. So just 3 times. So now after the third time, when it's called, now it doesn't go into the if condition because now X is 3. Right? X is 3. Right? It must be less, sorry, X is, because X plus plus is there, first time X is 2. Second time X, first time X is 2. Second time X is, sorry, first time X is, first time X is 2. Second time is X is 3. So therefore it again call it. So the next time X is 4. Right? So when you call the foo method for the last time, X is, sorry. So here X is 1. X is 1. When you come to the method, X is 1. But when you call itself, now X is 2. Right? So when you come to this one, X is 2. Now again it call it. But when it comes here, it is X is 3. X is 3. So when X is 3 also it calls. Right? So first time, second times, X is 1, X is 2. How many times we got the foo method? Foo. 1, 2, 3. Right. So first time X is 1, but it got incremented here, then call. So therefore X is 2. 2 is less than or equal to 3. Then X, it incremented to 3. Now X is 3. You call it. call it again. X is 1. When you call X is 2, X is 3. So there must be another call, right? Because less than or equal to 3. But inside it become 4 now. Right? When you call the method, X is 3, but inside X become 4. So therefore it doesn't come here. Now it doesn't come call itself, because once you get to the method, it already initially it becomes 4. Okay. So therefore it doesn't call itself. Now, because it's not calling itself, it start returning like this. And then it comes to my original test class. So therefore it prints 3 times and then gracefully terminate the execution. Okay, so that is why we got it 3 times. So that is one way, having an instance variable or static variable if you are not calling it through object. Okay, so the second approach is you can control the number of times this is getting executed. Now you can see we have a way out condition. It's very important that you have to understand that there's a going like that and there's a returning, right? Returning. So you can understand the returning by having a S out somewhere here, because it. So let's say by. So you will see these returns, this statement only at the end, right? After all the foo statements, then in the return statement, you will say bye. Okay. So let's look at that one also. You can see, so this is recursively calling foo method. Now we are in the return state, returning, right? In the return trip. So here you print once times by, then again by, then again by. So that is very important. Otherwise, you will never be able to come up with a solution or build a solution like that. So you must know that these are getting called at the end after recursive calls things, because that is the return trip. That is a return trip. Okay. Right. So that is one way of controlling the number of times it get called. So second approach is we can use a parameter, right? We can use a parameter. Actually, the second approach is the most widely used approach. So that is, so let's say this one as recursive basics 1. Okay. Right. So then we'll create another one, recursive basics 2. This one also I can rename as recursive basics 1. Right. So in recursive basics 2, what we do is we create a similar method called foo, which is an instance method. But now I will be introducing a variable, parameter, say int x. Okay. So now we change x, but the control is done through the parameter. Okay. So we are calling the same method, but with new parameter. New parameter, new value of the parameter. So that is the second approach. So there we don't rely on instance variables. Okay. So now let's create a test class for that. Test 2. I'll call this one also recursion basic test 1. Right. So in test 2, we'll do the same thing. Test 1, this one. Only thing is internally, how we implement the recursion is now different. Okay. So basics 2, basics 2. So now, why there's issue? So it must be recursion. Okay, psi OI. So now we have to send parameter. So we'll say now we are sending something like 1. Okay. So now we are calling with 1. It will become 2. It will print foo. Then it will become 2. And calling it again with 2. Next time with 3. Right. So then next time it is 4. Therefore, it will not call itself again because it is not less than or equal to 3. Now it will start the return trip. So the same diagram will be there. Okay. Right. So let's run it. Right. You can see you got the same output. Right. 3 times you got foo, 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 and then bye, bye, bye. Okay. So this is more practical approach because we don't rely on instance variables, rather we rely on the parameters. Okay. But it has a way out. That is, when the if condition is false, it stops calling itself. By the time the problem must have been solved. Okay. By the time the problem must have been solved. So that is the idea behind recursion. But still we haven't solved a practical problem. But that is the idea. Either you have to control the way out using an instance variable or using parameters. Okay. Now let's see 1 or 2 practical problems that we can solve using recursion. And you know the most popular problem that we already discussed in semester 1, that is calculating factorial. Okay, so let's do that first because we did it in semester 2, semester 1. Say factorial. Right. So there, let's create a method void, say factor something. We'll rely on the parameter approach. Okay. So that means we will send int x or something. Now you know how the factorial work. So factorial of 1 is by definition 1. Factorial 1 is by definition 1. Factorial 2 is 1 into 2 or 2 into 1. Factorial 3 is 1 into 2 into 3 and so on. And you can see there's a pattern, that is factorial 4 is 1 into 2 into 3 into 4. That is factorial 3 into 4. So I can write factorial 4 as factorial 3 into 4. Factorial 5 as factorial 4 into 5. So factorial n as factorial n minus into n. So that is a recursive nature. So if I want to find factorial n, I have to find factorial n minus 1 and then multiply it by n. So you can keep doing that, but by definition, factorial 1 is 1. You can't say factorial 1 is 1 into factorial 0. There's nothing called factorial 0. So factorial is defined only for positive numbers. Okay. Sorry, factorial 0 is by definition 1. Sorry, factorial 0 is by definition 1. Okay. So therefore, we can't do something called negative factorial. So therefore, we have to stop this recursion when we get into the factorial 0. Okay. So that is the idea. Right. So what now we can see that it's recursive in nature. If you want to find factorial 5, first I have to find factorial 4 and then multiply it by 4. But in order to find factorial 3 or 4, you have to find factorial 3 and multiply it by 4. In order to find factorial 3, you have to find factorial 2 and multiply it by 3 and so on. So let's implement that. Of course, you can implement it using for loop as well. Right. But if you want to use it recursion, so this is how you do it. Say we can even directly call return, say x into Now I want to calculate factorial x minus 1. So fact, I'm calling itself x minus 1. But this is never ending because why is that? It must return integer. Okay, integer. Right. So now the issue is this is happening for even after 0 also it is going to -1, -2, -3. It's a never ending recursion. Right. So we have to stop at 0. Right. We have to stop at 0 when we get x as 0. We have to say it is 1. So therefore we have to do that also. Say if, otherwise it's never ending, x is not equal to 0. Okay. And then do this. Then do this. Else, we can simply return 1 because factorial 0, that means x is 0. So now we have return statements in both sides. Okay. Now we can test this. Of course, we can call it as an instance method as well because we have make it an instance method. Okay, so therefore let's say factorial test. PSVM factorial f equal new factorial, and I will call the fact method. Say I want to calculate the factorial of 5, and it will return. So therefore I will have to take it to a variable. Say int r equal. So let's print it. R. Or you can say int, say seed value s equal 5. Then we can send s to make it a little bit more sophisticated, right? So now I can see factorial of s is, just to make it right, r. Okay, right. So let's run it. It says factorial of 5 is 120. Yes, right? 5 into 4, 20, 20 into 3, 60, 60 into 2, 120. 120 into 1 is 120. So you can see that we got the answer, but we use the recursion. So basically it called the fact method with 5. So then it calls itself, of course it's the same method, though I draw it separately, with 4. The same method with 3. Let me erase this. So if you understand this only, you can solve problems using recursion. Okay, otherwise you will not be able to solve problems. You may just know what is factorial. Sorry, just what is recursion. 5, 4, 3, 2, 1. Now when you get 1, next time you are returning it as 0. So calling it as 0. Now when you call it as 0, it is not equal to 0. That means it goes to the else. Now it returns 1. Now 1 into, previously it is 1. 1 into 1 is 1. So now this is also returning 1. Now previously it was 2. So 2 into 1 is 2. Right? 2 into 3, sorry. We increment every time by, we decrement every time by 1. Yes. So factorial 0 is 1. We return 1. Then 1 into 1 is 1. 1 into 2 is 2. 2 into 2 3 is 6. No, sorry, no. Factorial 5 is 5 into 4 into 3 into 2 into 1. Yes. So 1, we return 1. 1 into 1 is 1. 1 into 2 is there. Then 2 into 3 is there. 2 into 3 is there. Then 3, sorry, 1 into 2 is there. 1 into 2 into 3 is there. 1 into 2 into 3 into 4 is there. Then 1 into 2 into 3 into 4 into 5 is there. So that is how it returns. Okay. So every time we multiply our value by previous value. So basically, so this is returning 1. So this return 2, 2 into the previous one, right? 3 into the previous one, 4 into the previous one, 5 into the previously multiplied one. So therefore, finally we get the factorial 5. Okay, factorial 5. So that is how the problem is solved in a recursive manner. Okay, right. So this is a one type of recursion. So this is called tail recursion. Why? Our return statement is pretty much the last statement because it's in the last statement. So there's nothing after this. There's nothing after this. So if you have anything after this, then it is not a tail recursion. So likewise, there are different type of recursions that we can do. So this is the simplest possible recursion we can do. Okay, we can do. So now you can think of what are the other problems we can solve using recursion. So one problem is, yes, factorial problem. Right? Factorial problem. So another problem we can solve using recursion is, for example, if someone asks, you want to find a to the power b, right? A to the power b. So of course we can use loop. First, solve this using a loop. Okay, solve this using a loop. So that means you need to have method, 2 parameters, right? 2 parameters. So the method must return a to the power b, 2 integers and return integer. Okay, and it must return a to the power b. You can use a loop. Okay, so then you have to implement it using recursion. Using recursion, right? So take it as exercise. I will give you maybe 3 minutes to do it because 3 minutes is enough, right? Because you have to do it, right? This is programming subject, data structures. No point me solving problems. You must start solving problems now. Okay, right? Do it. So you must be having your Java running. If you want, you can just post it to the WhatsApp group or to the Zoom chat. Otherwise, you go to the exams without you solving any of the problems using recursion. So then how can you, of course, one thing is the exam, other thing is you will not be able to develop software because you don't know how to solve problems there. Right. Take about 3 minutes. I will write the method structure, but not the code. Okay. I will call it power. Right. First one I will call power non-recursion. Second one power recursion. Okay. Say power loop. Other one is power recursion. So I have two classes. So this is my power loop. It has int method called power. Say int a comma int b. You want to return a to the power b. Okay, a to the power b. Using a loop. For the time being, I will return -1. Otherwise, I get errors. It's my test class. Power loop. Say I want 5 to the power 3. It must be 125. Then I will just print it. Right, so it must return 125. Okay, if you implement it properly. So that is using the loop, no recursion. So then you have to implement the same thing using recursion. This time using recursion. That means you have to call yourself. So those are the two methods. Same results you must get. Okay. So you must return a to the power b. A to the power b. Using a loop, using recursion. Right. So how to implement using the loop? So easiest thing is for loop. Right. For say int I equal 1. I is less than b because I have to do it b times. I plus plus. I plus plus. What I have to do? So I will take a variable here because otherwise it will go out of scope. Int r result. So that is result equal I'll take it as 1 for the initial result into b, result into a, or I can say multiply equal a. So that is also possible. So okay, so let's do it like that. Multiply equal, because that feature is available in Java. So you have to do it b times, right? B times, sorry, not a. Yeah, a, b times. So that is b, this is my a. If 5 to the power 3, 5 in initially 5 into 1, then next time that into 5, that into 5. If b is 3, this loop will happen 3 times. And then we can return it. Return the result. Right. So now I can test. So, okay. Our loop test. I'm sending 5. I must be getting 125. Okay. Oh, why is that? 5 into 5, 25. So what's wrong? Because I initialize it to, no, 1, then 2, Yeah. So then 3. So first I will be 1. So first time the loop executes, then my results will be 1. Result is 1. So next time I will be 2. So therefore again it will be multiplied by A. A is 5. 5 into 1 is now 5. Right. So then it will be 3. 3 is not less than 3. So therefore it don't count. So therefore it must be what? Less than or equal to B. Right? Less than or equal to B. Not less than B. Right. So now it should work. Okay. Right. So now let's see something like 2 to the power 10, which must be 1024. Right. So it's work. Okay. So if you say 10 to the power 10, you must get 1 and 10 zeros. Okay. 10 to the power 10, 1 and 10 zeros. Oh, why is that? Is it because this is too much for integer? Yeah, but let's say something like 5 zeros, 10 to the power 5. Yes, I think that int variable is not good enough to keep 10 zeros. So then I have to go for something like long. Right. So it works. Okay, it works to 10 to the power 5, 5 zeros. Okay. Uh, right. So now you have to implement it using recursion. So this is non-recursive approach, right? Non-recursive approach. So now you have to implement it. Even the factorial, you can implement it using a loop that to do it as exercise, right? So now implement this function, the power function, using recursion, right? Do it. Because you have to solve problem. This subject is about you getting the problem solving abilities, right? Not me getting. It's not about you memorizing problem solving, right? It doesn't work. Okay, right. So let's do it. I didn't get any answer anyway. Right. So we have to get a to the power b. That is the idea. A to the power b. So this is one of the easiest one. Okay. A to the power b. So how do you do that? So you have to multiply a into a into a into a until we get into the b times. Okay, b times. So when you get into the b times, for example, we have to keep multiplying, say 3 to the power 5. So you have to do it 3 into 3 into 3 into 3 into 3. When you have 5 times, we have to stop it. Right? We have to stop it. Okay. So how can we do it? So any idea? Should we go for instance variable? Can we manage it with parameters alone? So with the instance variable, we can, but I'm just looking at whether we can do it without instance variable. Yeah, maybe we can do it without instance variable. Okay. Right. So we'll do something like this. So this is my happy path. A into A. But I will do this if my B is greater than 0. Okay. Greater than 0. Sorry. A into, I'm calling this one again. Power A comma B. Okay. A comma B. I'm calling itself, right? I'm calling itself, but I multiply it by A. But I do this only if B is greater than 0, right? B is greater than 0. But every time I'm going to decrement B by 1. So that means if initially 5, next time it will be 4, 3, 2, 1, etc. Okay, etc. And if not, that means if B is less than or B is not greater than 0, that means B is 0 or less, I will return 1. Else, should I return 1 or should I return the final answer? Or maybe I don't have to do anything, right? But I need a return statement. So now, first time I will be calling like this. Say 5 and 3. Next time it will be 5 and 2. Next time it will be 5 and 1. Next time it will be 5 and 0. So here I will be multiplying the current, the 5 and previous answer. Okay. But this time when it is 0, yeah, maybe we can set it 1. Right? Set it 1. Yeah. So we can set it 1, right? It will work. So we have to think about it. Right? Return 1. Because return trip, the other things will be calculated properly. Return 1. So is it going to work? It looks like for me it's going to work. Okay. Because this will be returning 1. Because minus B will make it, when this is 1, this will be 0. So when it is 0, it won't come here because it's not greater than 0. It will return 1. So then the previous one will return 1 into A. That is 5 into 1. The previous one will return again 5 into previous result, 25, and so on, right? So yes, it should work, right? Okay, let's see. If there's a bug, we'll fix it. Right, so this is power recursion. Right, so we are calling power recursion. And let's see whether we get 5 into 5 into 5. That is 5 into 5, 100, 50, 25, 25 into 5, 125, okay? Right, we got 125. Okay, so let's send 2 to the power 10. Now we are calling the recursive version, right? Recursive version. You can see recursive version. And yes, we got it 1024. So what about 10 to the power 5? Say 10 to the power 6. We must get 1 and 6 zeros. Right. 6 zeros, correct. Right. So I just solved 2 easy problems for you to get some idea about what is recursion and how can we use recursion to. So it's very important that you have this view, right? This view. You have to first visualize this solution. Then only you can make it to a code. You have to visualize what you are doing. Okay. So this return trip, you have to keep track of what happens, and you have to make sure that ultimately the recursive call get ends, okay, way out condition and so on. Okay. So it's not easy thing for initially, but with your experience, right, you should be able to build solutions using recursion. Right. Right. For this kind of problem, of course, the recursion is sort of overhead. But for complex problems, the recursion can be really handy, right? Because sometimes rather than using loops and so on, the use of recursion is pretty powerful. Okay, right. So now let's move on to our note. I will be using your university note, okay? So that is easier. Recursion. Now you must have a good understanding about what is recursion is, okay? Right. So recursion is a method calling itself. Okay, method calling itself. So you have to have 2 parts. Usually recursion is called in if-else condition because one part is the recursive call, other part is a way out condition. Okay. So it's a theory part. It's talking about how the method calls are done. Okay. I don't know why they're explaining so much of things. Okay. Right. So recursion, that now only they start about the recursion. Recursion is the calling of the method that happens to have the same name as the caller. So that is your calling itself. Okay. Right. So this is what I did. X to the power n or a to the power b. Okay. So this is what I implemented using recursion. Okay. Using recursion. So we must have the recursive call, but it must be called conditionally. So there must be a way out condition. Otherwise, it will be never ending recursion. Okay. Right. So these are the different types of recursion: the tail recursion, non-tail recursion, indirect recursion, nested recursion, and excessive recursion. Okay. So what I did, both the cases were tail recursion, right? Tail recursion. Right. So let's look at what is mean by tail recursion and so on. So tail recursion is the easiest one. So tail recursion means your recursive call is your last line or the last statement. It can be if-else statement, but it must be a last statement. And after the recursive statement, there must not be anything else. Okay. So the tail recursion is characterized by use of, let me highlight that. Use of only one recursive call. So we call it only once. You can see this one, this method. Sorry, the recursive version. Let's go into the factorial. Right. So you can see we call the same method only once, and that is in the last statement. So this is my last statement, if else statement. Okay. Not necessarily at the end, but last statement. Of course, this one has only one statement. Okay. So it must be in the last statement and you must call it only once. So then we call it tail recursion. Tail recursion. Okay. So in other words, when the call is made, there are no statement left to be executed by the method. That means in the return statement, you don't have to do anything. You mustn't do anything else. Okay. Just you keep returning. Okay. So something like this, you can see, this is your recursive call, right? Recursive call. You can see, this is my recursive call. It can be a return or it can be non-return. Sometimes you can implement recursion without returning. Okay. Right. So if it is tail recursion, definitely we can implement using loop. So that is something you have to understand. Anything that you implement using tail recursion can be implemented using loop. But there are, if it is non-tail recursion, it may be implemented using loop or may not be. There's no guarantee. But if it is tail recursion, definitely it can be implemented using loop. So that is why I told you that the tail recursion is the easiest one, because it can be even implemented using a loop. Okay. Right. So then we have the non-tail recursion. So in non-tail recursion, after your recursive call, right? After your recursive call, you may be doing something else also. You can see. So that means in the return statements. So when you return trip, you have to do these things. So in the every return trip step, there's something to be done. Maybe something to do some more processing. Okay. So this is just printing something, but it can be even some more processing. So then it is non-tail recursion. Right? Non-tail recursion. So this non-tail recursion can be used to solve some problems. Okay, to solve some problems. Right. So one of the common problem you can solve using non-tail recursion is if you want to reverse something. Right. If you want to reverse something. Right. So this is a very famous question. They can ask it in the exams also. Say you enter something like 1, 2, 3, 4, 5. You want to print it as 5, 4, 3, 2, 1. Right? 5, 4, 3, 2, 1. So how can you implement something like that? Of course, one way is use of a loop. You take it to array, right? You take it to array and you print it in the reverse order, right? You can do it using a loop. But you at the same time, so do it as exercise. Of course, that is not a big thing. Even someone with basic Java knowledge must be able to do it, right? You can use a for loop to iterate it from the other. But we can use recursion to do that in a clever manner as well, where you call the recursive recursion to do that. Okay, so let me implement that because it's an interesting example. Say, I will call it reverse. Okay, reverse. So I need to have a scan object because I need to input it. Okay. So this get char will not work otherwise. So you have to implement the get char method. Say scanner s equal new scanner. You know what is scan object, right? Input data from command line. So you have to send system in because I'm using the console to input. Okay. Right. So now I will have a recursive method. Say void, say reverse or RVB or something rev. So here I will be taking the value from the user. So how to do that? I will take it to a char int ch equal s dot next char. Right, next char. You don't have next char. Why is that? So let's do a search. How to get, maybe it's converted int char from char using scanner. Without next char. The one method it doesn't have is next char. Yes, that is my problem. Read line of text with scanner as you normally would do. Change the scanner's delimiter, blah, blah, blah. Okay, we'll take it to a string. Right. We'll take it to a string. Okay. String. Because we can take one character to a string. So then I can say next. Because next return a string. Okay. Right. So what I do is I take this to this local variable. This is a local variable. Okay. Then I call this method again. Okay. This method again. So that is what I'm doing. I'm not just take it to the local variable. Then I'm calling the method again. In the return trip only, I'm going to print this. Because in the return trip, then it will be print reverse order. So now, after calling itself, whatever here will be called in the return trip. So therefore, in return trip, I print it. Right? CH. Now, every method has its own local copy of CH because it's a local variable. So even though it's recursive, if I call the recursive method 5 times, each method call has its own CH, which we have already read. Okay, so let's use print rather than println. In the return trip, I'm keep printing the current value. So therefore, I will print in from the reverse order. Right? I'm reading, keep it there, reading, keep it there, but there's no way out condition yet. Okay. I read it, keep it there. Then I again call itself. So therefore, again I read it, keep it there. Again I read it, keep it there. Again I read it, keep it there. But now I need a way out condition. Right? Way out condition. Otherwise, we are keep reading, and not doing anything else. Right? So therefore, now we can come up with sort of a solution for that. Maybe we can say if you enter, right? If the user enter something like A, B, C, then enter, then we'll start the get out of the recursion and start the way out the return trip. So then what we have to do is remember never call this directly without a condition. Okay, so then I will say if so how to check whether it's a new line character? CH. Okay. Can we say something like equals? Or we can say you enter star or something. Okay. It doesn't matter. Or you can say compare case, new line character slash n, right? How to write it? It will return true, false. It will return. It will return. How do you know it is 0? Let me double check the code. String compare. It's okay. So this is how you compare. Zero if strings are equal, right? Zero if strings are equal. If it is not equal to 0, we'll call it again. Otherwise, you don't call it. So that means it comes to the way out. Okay, right. So let's see whether it's work. I hope slash n will work. So that means when the user enters enter character, it must stop calling itself and waiting for another input, because when you call itself, it's again waiting for another input. Okay, right. So let's run it. So let's call it reverse test. With PSVM. Reverse R equal new reverse. You just have to call rev. Okay, nothing returns and so on, right? So let's run it and see. Right, no prompt is given. That is okay. Right. So now I will keep entering. Say 1, 2, 3, 4. Enter. So why it is not printing? Okay, so don't try print it. Not equal. See. Maybe it is still waiting, right? Okay, so let's do a debug here and run it and debug it. Debug. Sorry, not this one. Let's close this. Right, so let's do a debug here. So let's get into next one. Step in. So now it's waiting for input. It's waiting for input. I put our debug here also. Here also, okay. Now I have to go and enter something. Say 1. It's not keep calling, right? Maybe I have to go to the debug. Nothing. Why is that? let's not have a debug point here. Maybe now I have to enter 1. So compare it, no case. It's waiting for enter, right? It's waiting for enter. So that is the issue. Now let's look at what is CH. CH is 1. Okay, CH is 1. Right, so we'll do something like that. If you get star, we'll stop it. Okay, right. So not enter because it's waiting for the enter. Right, so let's do something like this. So we'll stop it. If this is star, we will stop it. Okay, star. Right, so now let's run it. So that means if I type 1, 2, 3 star, it must print it in reverse order. Let's see. Okay. Say 1, 2, 3 star. Sorry, star. Now it prints 3 to 1. So that is the return rip. Okay. Because that next expect you to enter also. So let's run it again. Right, I will type A, B, D, R, and star. So star is to fulfill the condition. So then it must print RDBA, right? RDBA, because it's happening in the reverse or the return trip, right? So we are each time we are keeping our character into a local variable, and that variable is waiting until the return trip is coming. That is why your memory has a stack area. Remember we discussed that in semester 1. The memory has a stack area. So stack area is keeping track of all these local variables, right? So until it's waiting for the return trip. So when it return only, that stack part, that memory is released. That memory is released. Okay. So it keeping the character each time, and in the return trip, it keep printing. Of course, therefore it is printing in the reverse order, right? So that is not non-tail recursion. Why? Because after the recursive statement, in the return trip, it has something to do, right? It has something to do. Okay, right. So that is an example of a non-tail recursion. Okay, of course, you should be able to do it without the enter also. I think the note has that kind of example, but I just use the star to detect you are done. Now you want to the reverse string. Okay, right. So that is how non-tail recursion works, right? So now you must know what is tail recursion. So you don't have anything after recursive call. Non-tail recursion, there can be something printing or some processing after in the return trip. Okay, in the return trip. Right. So then we have indirect recursion. So indirect recursion means you are now earlier we just our F is calling itself. F is keep calling itself until the condition is satisfied, fail. In non-indirect recursion, maybe A is calling B is calling C, and C is calling A. So therefore, again the recursion is there, but indirectly. Not A is calling A. Maybe A is calling B, and B is calling A. Or A is calling B, B is calling C, and C is calling A. Something like that. So then we say it's indirect recursion, right? Indirect recursion. So ultimately, it's getting called itself. Okay, so that is very rare actually, but there can be situations like that. For example, if you look at something like our in the microprocessor, we have fetch, decode, execute. But after execution, again it calls fetch. So it's also something like indirect recursion, but of course that is happening in the microprocessor level. So therefore, sometimes we have to do like that also. Maybe you get something, process something, send something, again you have to get something, right? So as long as, of course, again you need to have way out condition. Maybe if you find that nothing is there, you can stop it. But as long as you have something in the buffer, you have to do it. So that is called indirect recursion. Okay. Right. So you can see receive, decode, store. Right. Again, you have to receive. Right. Decode, store. Again, you have to receive. Maybe if receive has nothing, you stop it. That is you way out. Okay. That is called indirect recursion. Okay. Indirect recursion. So then we can have nested recursion. So the nested recursion means in your recursive call itself, you are again calling itself, right? So how, I don't know whether you get it, right? So here you can see you are calling itself, but to calculate another parameter, again you are calling itself. So that means you call A again, but to calculate a parameter for A, again you are calling A, right? Again you are calling it. So that is very rare, but that is possible, right? So, but also used in one parameters, at least in one parameter. So which a function is not only defined in terms of itself, but also is used as one of the parameter. To calculate the parameter also, you need to call itself. So while you are calling itself, you need to calculate a parameter. To calculate the parameter also, you need to call itself. So that then we say it is nested recursion. Okay, nested recursion. So which are very rare, but there can be, especially in mathematical sequences and so on, that kind of recursions may need it, right? For example, you can see H2 is H2 plus H4, right? So then H4 you have to calculate as H2 plus H8 and so on. So it's a nested recursion, right? Nested recursion. So don't worry, you don't have to implement that kind of things. Of course, if you want, you can implement, but there are the practical problems we can solve are very rare unless it is a complicated mathematical problem. Okay. Right. So that is nested recursion. So this is another example of a nested recursion. You can see. So you are calling itself, and to calculate the second parameter of A, because it has two parameters, to calculate the second parameter, again you have to call itself. So that means it is nested recursion. Okay. Right. So then we have the excessive recursion. Right. Excessive recursion. So excessive recursion means something like, right, you are calling yourself more than once. Right. In the recursion, you call it. So it's something like it's going to different paths. So far what happens is you call it like this, then you return. Right. Then you return. But in excessive recursion, what happens is you call this way, and also you call this way. So this keep going and come back. Then you have another path to go and come back. When both paths are done only, you are done. So then what happens is that is also not the end of the story. So you call this, and then this guy calls this, and this guy calls this. Then return, you have to go like this because there's another call. So then when this return, you have to call like this. Maybe this one you have to call like this. Then this one you have to call like this. So then here also you have to call something like this. Then this has to call like this. So this has to call like this. So that is, then you can see it grows like a binary tree. So that is why we are doing recursion before binary trees. And even it can be binary or maybe three. So you have 1, 2, maybe another one. So then you have another path. So then each one has 3 paths and so on. So then we call it, it's sort of a growing like an exponential way. Of course, at a time you are in one place. For example, you go there, you go there, you go there, come back, then you go there, come back, you go there, come back, then come back, go there, come back, go there, come back, go there, come back, come back, come back, then only you are coming here. And that is how it's happened. Don't think that these are parallelly happening. Right? But at the end, it's like a sort of a tree. Sort of a tree, not sort of a tree. Actually, it's a tree. Right? It can be a binary tree if it is 2 methods calls, or it can be more than 2 branches are there. 3 branches, 4 branches. So that is called excessive recursion. Okay, excessive recursion. And we will be using excessive recursion in binary trees. So that is why we are interested in recursion before getting into the binary trees. Okay. Right. So that is excessive recursion. Okay. So this is a very famous example for excessive recursion, that is Fibonacci numbers. It's a special type of series in mathematics. You call it Fibonacci numbers. Right? So it's a very good exercise for you guys. Use this definition and see whether you can get the next number, next number, next number, next number. For example, if n equals 0, obviously, when n equals 0, it is 0. So therefore, it must be 0. Right? It must be 0. That is self-explanatory, right? So that is self-explanatory. It must be 0. So then when n equal 2, what happens? Sorry, n equal 1. So now n is not equal to 0. You have to come here. So when n equal 1, it must be Fibonacci 1 minus 2, which is minus 1. 1 minus 2, which is minus 1. Plus Fibonacci minus 1 minus 1. Sorry, we have n equal 1 now. 1 minus 2 is minus 1. 1 minus 1 is 0. So Fibonacci 0. And Fibonacci 0 is 0 by definition. So this is 0. So then this one is minus 1. Minus 1. Sorry, for first two numbers, by definition, we have it. Okay, sorry. That means when n equals 0, it is 0. When n equal 1, it is 1. By definition, it must be there, because otherwise it get into the negative numbers. So therefore, by definition, this is also 1. Okay, this is also 1. So they have asked this in the exam paper also. Right. So therefore, by definition, these two values are there. Okay, because this is 0 and this is 1. Now you can start calculating the rest of the stuff. For example, if you have n equal 2, n equal 2 means not come here. And that is Fibonacci 2 minus 2 is 0 plus Fibonacci 2 minus 1 is 1. And Fibonacci 0 is 0 plus Fibonacci 1 is 1. So therefore 0 plus 1 is 1. So therefore this is 1. Now you can calculate n equal 3. N equal 3 means not this one. Fibonacci 3 minus 2 is 1. Fibonacci 1 plus Fibonacci 3 minus 1, 2. And we know Fibonacci 2, this is 0, 1, 2. Fibonacci 2 is 1. Fibonacci 1 is also 1. So therefore 1 plus 1 is 2. Likewise, now you can keep calculating the rest of the stuff. Okay. So sometimes they will give you the Fibonacci series not to implement. And if they will ask what is Fibonacci 4. So then you have to start with 0 and 1. And then you have to calculate next one, next one, next one, and find out what is this. Okay. In the exam. Right. So that is a famous example for excessive recursion, because it grows like a tree. Okay. Like a tree. Right. That's it about recursion. Right. So we'll take a break. After the break, we will look at analysis of algorithms. Okay. So let's continue. Analysis of algorithms. Okay. So we'll be using our note first, then we will be using the university note as well. Okay. Right. So what is mean by analysis of algorithms? Now we have discussed about some sort of algorithms, right? So for example, for stacks, the push method, pop method, peek method, and then linked list, traverse method, insert method, delete method. Today we discuss some more algorithms like calculating recursion, right? Fibonacci series and so on. And now you can see that when it comes to a problem, there's nothing called only one solution, right? So we can solve the same problem in different way, right? For example, we can solve the concept of stack using either linked list or using array. Right? We can calculate factorial using a loop or using a recursion. So there are multiple possibilities. And when it comes to complex problems, the number of solutions are also high. For simple solution, mostly we can see only one solution because other solutions obviously will look overcomplicated. But for complex problems, definitely there are more than one way of solving. For example, there are so many different searching techniques, different sorting techniques, right? Bubble sort, uh, cage sort, and so on. Okay, exchange sort. So ultimately, we are doing the sorting. So therefore, when it comes to algorithms, how do you know whether it's a good algorithm? Okay, so there are two things we have to look. Number one is it does the work. We call it effective. Effective does the work. It does, of course, if not, no point talking about that. Right? So number two is maybe there are 3, 4, 5 algorithms, it does the work. Now, how do you determine which one is the best? So then another factor is efficiency. Right? Efficiency. How quick it can do the work. So that is what we'll look at in analysis of algorithms and BIT-UOC notation. Right? First of all, it does the work effective. Of course, otherwise no point talking about it any further. Second one, is it efficient? Because if it is efficient, it takes less time to execute and get the result. But those are not the only two things. There are some other things as well, like is it a general solution? Is it reusable? And so on. But those are secondary things. The two key things are effective, efficient. So then we say it's productive as well. Right. So let's see how can we say it is efficient. So the number one is if it returns the result fast, quickly, it is efficient. That is time efficiency. But there's another aspect of efficiency. We call it resource efficiency. So resource efficiency means if it takes less resources to solve the problem, maybe less memory, less processing power. So that is also good. Because sometimes the computers struggling with resources, right? So when it's need more resources, sometimes it will be slow as well. So therefore, we are interested in time efficiency and resource efficiency. But in this topic of analysis of algorithm, of course, that is related to efficiency, we will be more interested about the time efficiency. Okay, time efficiency, not the resource efficiency. But in the exams, they can check whether you know both. Okay, but we are more interested in time efficiency. So how do you find efficiency of algorithm? How do you find efficiency of algorithm? There are two ways. First approach, we find the efficiency of algorithm by testing. So we run the algorithm 1 for the same set of data and see how long it takes to return the value or give you the result. Say it took 1 second. So then we use the second algorithm for the same data and calculate how long it takes. Say it took 2 seconds. And now we know that. So this one is faster. Okay, so that is one approach. So second approach is we don't run it, right? We don't run it. Rather, we analyze the algorithm and determine which one is faster, which one is more efficient. So that is what analysis of algorithm is. So we analyze the algorithm and determine which approach, which algorithm is faster. Okay. So then someone will ask which one is better. So the better approach is analysis of algorithm and determine the efficiency rather than running, because running algorithms and determining the efficiency has a lot of practical issues. One thing is computer is a multitasking, multi-purpose, especially multitasking device. So therefore, when you're running your program, it is not only your program is running, so many other threads are running. Because we never know at that time how many threads sub-processors are running. So therefore, these time results are not very comparable, because at that moment maybe your computer is in a different sort of a situation. So it's very difficult practically to get this ideal situation for two instances. So therefore, these calculations are not very reliable. So that is the main issue. It's not like measuring using a beaker or something, like measuring beaker or something like that, because computer is complicated multitasking device. So therefore, usually the results we obtain by analyzing the algorithm is more reliable. The second thing is, even before implementing, we can analyze the algorithm, not the implementation. Algorithm itself we can analyze without implementing. So that means before implementing all the approaches, we can analyze and determine, okay, this approach we will implement. So, and also it is neutral of your language. Of course, you can analyze it with respect to the language as well. So likewise, there are a lot of advantages as well. And the other thing is, when you get used to the analysis of algorithms, what happens is, you know what kind of things make your algorithm faster, what kind of things make your algorithm slower. So that you can unconsciously use when you come up with new algorithms. So when you are asked to come up with an algorithm to solve a problem, so if you are experienced in analysis of algorithms, you know where the bottlenecks are, where the efficiency is compromised. So therefore, when you have set of solutions, you naturally pick the best solution because you have that experience. Okay, so likewise, there are a lot of advantages of knowing how to analyze algorithm and determine the efficiency of different algorithms. Okay, right. So that's the objective of this topic. But before moving to that, the how to practically analyze algorithms, anyway, we are not going into great details. So let's look at a little bit of mathematical background. Okay. So you must have the basic understanding of some of the graphs. So that is why we have done, that is one of the reason we did algebra in semester 1 maths. Okay. Right. So what are those graphs that you must know? First one is, if you have a straight line like this, like y equal 2, right? Y equal 2. Now you can see that even though x vary, say x is 1, x is 2, x is 3, and so on, y is the same. So y doesn't change, right? So that understanding you need to have. Okay. So say this is, we are doing and we are analyzing a algorithm for sorting. Say for when we have 3 data to sort, say it take 5 seconds. Say when we have 100 data also, it take 5 seconds. So that means the algorithm is not depending on number of data. So then it's something like this. So even though you increase the number of data, say this is the time, so this is number of values, data. So even though you increase the data, the time taken is not getting increased. So then we say it's in something like constant function, right? Y equal k, y equal c. Okay. So next one is y equal x, something like this. So that means when x increase, proportionately y increase. For 3, if it is 3, for 6, it is 6. So when you twice x, your y is also twice. So that means if you have algorithm like that, say for 1000 data, it take 10 seconds. So then 2000 data, let's say it take 20 seconds. Okay. So y equal x is a special case where 1000 data 1000 seconds, 2000 data 2000 seconds. But maybe it is not y equal x, maybe it is y equal half x, y equal 0.75x and so on. But you can see it's sort of proportionate. So this is y equal x or y equal mx line. M can be 1, m can be greater than 1, m can be 0 to half, 0 to 1. So this is more than 1, but not negative. Okay. So now we look at two things. Y equal c, y equal mx. Okay, y equal mx. So another one is y equal x squared. Something like this. Of course, this side it's something like this. Let's look at only positive thing because this axis we will consider as number of data. So number of data won't be negative. So therefore, we are more interested about this part. So this is y equal x squared. So if y equal x is something like this, y equal x squared is something like this. Earlier, this is below, but after sometimes this is growing faster. For when x is 5, here 5, but here it is 25. Y equal x, when x equal 10, it is 10. But x squared, when x equal 10, it is 100. Right? So that is y equal x squared. Okay. So then we may have something like 2 to the power x. Not x squared. 2 to the power x. So that is even steeper curve, like something like this. Something like this. It's grow very fast. It's grow very fast. It's grow faster than x squared. Okay, x squared. And then we have another interesting one, that is log n. Log function. So log function initially grows fast, but then it's growing, getting lesser and lesser. Something like this. So then you have n log n, which is not as good as on. Okay, because it go beyond that. That is the time taken. It is good for lesser number of data, better than on. But after sometimes it is getting worse, but it is not as worse as n squared or 2 to the power n. Because you can see this is getting a lot of time after few data. So what you have to do is you must have relative idea about these functions, relative idea. Right? For example, if it is something like this, it doesn't depend on the data. Always it takes the same time. So this one is really good one. Of course, these algorithms are very rare, right? Very rare, but there are, because that is superb algorithm, because your time taken does not depends on the data, the amount of data. And the next best is this one, log n. If you have algorithms where the efficiency is log n, it is not as good as a constant, but it's growing very slowly, very slowly. Okay, so that is the next best algorithm. So then we have y equal x or y equal mx algorithms. So they are growing, but proportionately. It's not that good, but compared to other three, it is better. So the next better thing is n log n or x log x algorithms. It's worse than on, but better than the other two. So n squared is even worse than x log n, n log n or x log n. So this we take it as a number of elements. And the worst one is 2 to the power n. Out of these, of course, it doesn't mean that only these type of functions or algorithms are there. There are some different algorithms, but these are some commonly found functions which determine the efficiency of algorithm or resemblance the efficiency of algorithm. So what are those? Constant function, k, log n, n log n, n squared, 2 to the power n. So if I take n as the axis, okay. So you must have that in your mindset. What is the shape of these? What are the shape of these functions? So therefore, then you know that if someone says my algorithm is n, it is not as good as log n algorithm, but it is better than n log n. But n log n algorithm is better than n squared, but n squared algorithm is better than 2 to the power n, and so on. Okay, right. So that is the mathematical understanding you need to have. The shape of these functions, relative shape actually, right? You don't have to precisely draw it, but relatively, you must have that in your mind. Okay, that in your mind. Right. So when it comes to analysis of algorithms, there are different ways you can look at it. One way is we look at the worst case scenario. Right? Worst case scenario with lot of data. Another thing is you look at the best case scenario. The next one is average case. So forget about the data. So what are the three possibilities? You look at the worst case, how long it will take. Or best case, how long it will take. Or average, how long will it take. Okay. But usually the most popular one is worst case approach. Because if worst case we can analyze things, definitely it is going to be better in average and best cases. So therefore, when we compare algorithms for their efficiency, we compare for worst case, what is the relative efficiency of algorithm A compared to algorithm B. Okay, so therefore, this is what we are really, really interested. Worst case scenarios. Right? Worst case scenarios. We compare algorithms on worst cases. Okay. If algorithm A is better than algorithm B in efficiency in worst case, we will pick A as our preferred algorithm. Okay, preferred algorithm. So how do you determine the worst case? So usually for algorithm, especially data-oriented algorithms, the worst case is, for example, if you take searching, right? You are searching a value. There's a set of data in array. You want to see whether particular data is there. You are going to search it from this end to that end. So what is the worst case? Anyone? What is worst case scenario? The best case is you found the data in the first element because you are searching it from the first element to the last element. So what is the worst case scenario? Worst case scenario is either you found the data in the last element or you haven't found the data, because if you haven't found the data, still you have to keep searching. Because if you found the data, you can return because you don't have to search anymore. They ask whether it is there. Yes, it is there. You don't search it anymore. So therefore, you can return. For example, if you are in a for loop, you can break the loop because no point wasting your resources, processing resources. You can just break it. But if you find it in the last one, so your loop is 100% executed. If it is 1 to 1000, it iterated 1000 times. And even worse, so same worse scenario is you don't find it because you can't say it is not there only after you come to the right end. So those are the two worst case scenarios. Right. So the most worst one, or out of those two worst cases, okay, but which one is the worst? Not found. Not found. Because you can say not found only after you exhaust it. Okay. So when it comes to analyzing data, we are interested in the worst case performance and also when we have a lot of data. Lot of data, worst case. That is what we are interested. So that is why when we are drawing these diagrams, we are interested not somewhere here. not somewhere here where we have little data. You can see almost all the algorithms look the same, but we are really interested what happens somewhere here. So this is good, this is okay, this is average. So now you can see these are really bad algorithms, right? So you can compare the efficiency when you have a lot of data. Of course, we can't go for infinite, maybe 1,000 or maybe 10,000, something like that. So that is where we are interested in which algorithm is better. Because that is what usually we have to practically use it. Because if with small number of data, maybe any algorithm is okay. Because we just have to do small number of processing. Okay. So therefore, what we are interested is worst case, large number of data. Okay. So in analysis of algorithm, we give them different names. So there's something called big O notation, little theta notation, and so on. So this is big O notation. That is why we say O1, O log n, and so on. So basically, we give the big O notation when we look at worst case lot of data, or at least worst case. Okay, worst case scenario. Okay. So therefore, if it is y equal x, we say it's O(n). So n is number of data. So it's O(n). If it is constant, we say O1. Rather than constant, we just say 1. So that is a convention we use, because sometimes it's just a constant, but we just say O1. Okay, rather than OC or something. So then if it is x squared, we say ON squared. O log n, ON log n, ON squared, or 2 to the power n. Right? So that is O means worst case scenario. Big O notation. That is the word we use, big O. Okay. Worst case. So big means we look at large number of data, and worst case. Okay. So then there is another notation for average case, best case. We are not that interested. So those are the theta notation, omega notation, and so on. Okay. Right. So what we are interested is big O notation. Okay. So in big O notation, of course, we don't calculate the efficiency exactly. We just calculate, we just do approximation. For example, compared to a big value, a small value has less significance. Right. For example, if you say Fn equal n squared plus 1 or plus 100, so this one has less significance for large n values. Of course, if n equal 1, this is 1 plus 100, 101. 101, and out of that 101, 100 comes from here. When n equal to, that is 4 plus 100, 104. Out of 104, 100 comes from here. So this has a lot of significance. But when n is bigger, like when n is 1000, and now n squared is this and this 100. Now you can see this has less significant compared to this. So you can see that for big values, this constant has no significance, because these guys have better significant, because these guys contribute to the final value than this one for bigger n. So therefore, if you have something like even n plus something constant, we just ignore the constant when you have n. Okay. So if it is a constant, we just call it 1. If it is n plus k, we just call it n. If it is n squared plus n plus k, we even ignore this one also. Because, for example, when n is 100, this is 1000. And this is 100, and this is maybe 5. So now you can see this guy is more significant than these guys. So therefore, for very large numbers, we can even ignore this one. Okay. So that is how we do. So therefore, if you have something like n plus k, we just call it n algorithm. If you have n squared plus n, we just call it n squared algorithm. If it is n cube plus n squared, we just call it n cube algorithm. That is just to make it simple, and because that is the most significant guy. Okay. So if you have log n plus something like 5, we just ignore that and say log n algorithm. Okay. So that is how we come up with the big O notation. A constant is considered as 1, and n cube plus n squared or something is considered as n cube. So that means the higher order only we take. So here we just take n4. We ignore the other thing. Constants obviously we ignore if you have n terms. Okay, and so on. Right. So what we are interested in is that big omega notation. Sorry, a big O notation. Okay. Big O. We are not interested in big omega, big theta, little o, and so on. So those are some other notation for other scenarios. What we are interested in is big O notation. So big O notation, we just do this approximation. What are those approximations? If it is any k value or c value, we just call it O1. If it is n plus constant, we just say On. If it is n squared plus n plus constant, we just say n squared. Right? If it is n cubic or something, n squared, we say On cube. And if it is, say, log n plus constant, we just say log n, and so on. So we just ignore the constants, and also we ignore the lower powers. Because for big values, higher power determines the final value. Right? So when you have billion, 1000 is it's not significant. The billion compared to billion. Okay. That is the idea behind big O notation. And you will find that there are some algorithms which are O1, that means it's a constant time, O1. Some algorithms are On, some algorithms are O log n, that is log 2n. Some algorithms are n log n. Some algorithms are On squared. Some algorithms are On cubic, and so on. So we have already seen O1 not algorithm, and On algorithm we have seen. So we will see log n, n log n. We can think about our n squared algorithm also. Right? On squared, n cubic as well. Right? So for example, remember we discussed about hashing. Okay. We discussed about hashing last time under database, right? Yeah, hashing. So remember, hashing convert a bigger range into a smaller range. And when you give the number, it gives you the location. So it doesn't matter whether you have 10 records or billion records, right? In your file, always you just give the hash function, and hash function says this is the block where you have the data. In this block you have the data. So it doesn't matter whether your hard disk has 100 megabyte of data or few terabytes of data. What you care is you give your number to the hash function, and hash function says this is the block. So therefore, it doesn't matter whether you have billion blocks, because as long as you get the exact block number, you just go there and get it. So therefore, you can see that hash functions are O1 algorithms. So remember, rather than constant, we say O1. That means it doesn't change. So it doesn't change with the number of data. Efficiency is constant. So that is why we really like hash functions, if possible, because it doesn't matter how many data. Okay. Because you just straight away go to the correct location. You don't search anything. Now you can see that hash functions are really good, if possible, because it's O1 notation, O1 algorithm. It doesn't depend how much data you have. You just go to the correct place. Your algorithm, your hash function give you the place. Of course, if there's a collision and so on, it can be little bit of inefficiency, but in general, it's very efficient. Okay. So now let's look at something like ON algorithm. Right? ON algorithm. For example, you are doing a linear search. So you have data in the array. So you just keep searching. Say you are looking for 50. So this is 10, 90, 35. It's not ordered. 80. 35, 50, 40, and so on. Say you are looking for, say, 80. So you have to keep searching because you never know where is it because it's not sorted. Maybe you found it. But if you have 6 data, worst case, for each look at you, it take 1 second, 1 millisecond. So the worst case, you need 1, 2, 3, 4, 5, 6 milliseconds when you have 6 data. What about if you have million data? The worst case, that is you don't find it or you found it at the last one, it take million seconds. Worst case, million seconds. Because after searching it, each and every entry only, you can say it is not found. Or maybe you found it as the last one. So now you can see that it is ON algorithm. Linear search is a ON algorithm. Right? So the worst case depends on number of data. Larger the number of data, the larger the worst case performance. So therefore, we say that linear search is a ON algorithm. ON algorithms are okay, but not as good as O1. O1, because in O1 algorithm, whether you have millions or billions or trillions, it take on the same amount of time. If it take 1 millisecond, when you have 2 data also, it take 1 millisecond. When you have billions data also, it take 1 millisecond because your hash function says go there and find it. You go there, if it is there, you say yes, found it. If it is not there, you say no, it is not there. As simple as that. So you can see that hash functions are O1 functions, whereas linear search is ON. ON is significantly less performing than O1. Okay. And later you will learn another search called binary search. Okay, so remember we have the searching and sorting algorithms, and you will find that binary search, this is a linear search. Binary search is log n algorithm. So log n algorithms are initially like this, but then it goes like this. So then you will find that for large number of data, binary search which has log n algorithm is better than linear search which has ON. This is O log n. And you will find why we call it log n when we are doing the binary search. So therefore, we would say binary search is better than linear search. Right? So similarly, you will find later, there's a sort called bubble sort. Bubble sort is ON squared algorithm. ON squared algorithm. It is even worse than ON. But again, you will find there's another. So this is ON. So this is bubble sort. Okay, bubble sort. So then you will find there's a sort called quick sort, which is n log n. So remember, this is log n, which is even better than ON. But n log n is something like this, n log n. And you will find that quick sort is n log n algorithm, or n log n algorithm. Quick sort. But this is bubble sort. And then you will find that quick sort is better than bubble sort for large number of data. Of course, it is not as fast as linear search, but sorting and searching is 2 different things, right? So therefore, you can't compare linear search and quick sort because sorting is one concept, searching is another concept. So you have to compare sorting algorithm with sorting algorithm. So therefore, we have 2 sorting algorithms called bubble sort and quick sort, and you will find quick sort is better than bubble sort. So similarly, there's a selection sort. There we say that selection sort is also n squared. So then we say selection sort is pretty much the same as bubble sort. But quick sort is better than bubble sort and selection sort. So that is how you compare algorithms. Okay. So then someone will ask, here we have only one loop. Right? So maybe just for loop. Worst case is you have to run the entire loop. So then someone will ask why this is n squared. You will find that in bubble sort, we have loop inside a loop. So for each iteration here, this has to go full iteration. So then next iteration, full iteration. So that is why it becomes n squared. So if you have nested for loop or nested loops, 2 level, it will be n squared. And actually, when you look at the bubble sort, you will find that we have to go through one loop. Inside that, you have another loop. So that means, yes, a bubble sort is n squared algorithm. If you have another loop here, it will be n cubic. But luckily, bubble sort is n squared algorithm. Okay. So likewise, there's a reason why we say n, why we say n squared. N means usually one loop. N squared means nested for loop. One loop inside the other loop. Right. And you will find that why we call it log n, because every time we get rid of half of it. So after first calculation, you get rid of half of that. Then after next calculation, the rest of the half again. So every time we get rid of half, you quickly get into the final answer. So that is why we say log 2n. So you know that log 2n 2 to the power has a relation. That is why you learn about inverse and inverse functions and so on, logarithms. So you get a better feeling about it if you know what is logarithms, what is index, right? What is y equal x line, what is a constant line. So that is why you learn. That is one of the reasons why you learn algebra again. So then you have a mathematical sense about what you are writing. Okay, what you are writing. Right. That's it about analysis of algorithms. Any questions? Any questions? No? Right. So then we'll move on to hashing. But anyway, hashing is not in new syllabus. Okay, new syllabus, because hashing is in your data. We already did the hashing in your database, the data management subject. Okay, data management subject. So therefore, they have taken it out. They have taken it out. The hashing. Okay. So now we did recursion. We have done recursion. We have done analysis of algorithms. So we have done these things. So we have trees, graphs, searching and sorting algorithms. Okay. But I will briefly mention again about hashing, very briefly, because it was in the old syllabus. You may see some past paper questions also. But anyways, all those things we have already covered. Okay. I have uploaded the hashing note also, the old syllabus note. Right. So what is hashing is, I told you hashing is superb algorithm if possible, but only thing is hashing is not going to work everywhere. Hashing is, as I told you, O1 algorithm. Right. It doesn't depends on number of data, because hashing algorithm just says go there and find it. Go there and save it. Go there and find it. Okay. So it's one of the best algorithm, but only thing is hashing is not going to work everywhere. Okay. Right. So in hashing, what we do is we map a big range into a small range. Maybe this is millions of data. Possibility of 1 million data. Okay. But maybe it is mapping it to one of the, say, 0 to 999. Right. So that is what hashing is. Maybe this capital N mod simple N. So therefore, when you divide by simple N, always what you get is 0 to N minus 1. If this is 1000, always what you get is 0 to 999. Right? So that is what hash function is. Okay, hash function is. But remember, when you map bigger range to a smaller range, there's a possibility of collision. If you do this one, even 55 will say mod 10, 55 will map to 5 as well as 75, because 75 mod 10 is also 5. Assume we have 0 to 9. That means the possibility of collision is there. Okay. So that you can't eliminate. But good algorithms, good hashing algorithms try to randomize it this way, that, right? So maybe 1 is mod to this, 2 is mod to this, 3 is mod to this, and so on. Okay. So then the other thing is, though we have a big range, we don't anticipate that though it is 1 to 1000, we anticipate that only 100 data will be there, or only 10 data will be there. Otherwise, anyway, there will be collisions. because you know that practically you can't keep thousands of data in 10 locations, right? But the idea is out of these 1,000 data possibilities, we at a time we will keep only about maybe 8 to 15 data. So that is where hashing works. Though there are possibility of 1,000 range of 1,000 values, practically, if you know that practically the maximum is 10. It's something like you have 100 friends, but you know that, let's assume you know that when you ask them for a trip, you know that only about 5 to 10 comes. So then you can map them without any issue, because you know that practically no way all 100 comes to the trip. So only about 5 to 10 comes at a day, on a particular day. But any of these people can come, but in general, you know that only about 5 to 10. So then you can happily hash it to something like mod 10. There can be collision, but rare. But yeah, there can be 1 or 2 collision in your mod function, because 66 also came, 800 and so sorry, out of 100, 66 also came, 36 also came. Now both are into the same 6 slot. But that is rare. Okay, that is rare, can happen. There's very unlikely that 6 came, 16 came, 26 came, 36 came, 46 came. No, right? Because that is very rare. Right. So that is what hashing function is. Right. So they try to randomize it, but possibility of collision is there. Okay. So we discussed some of the hashing functions as well. Okay. So something like the idea is make it random. Okay, make it random. So there are the most popular hashing function is mod function, the simple hashing function. So then you can go for mid square hash functions, extraction, radix, and so on. So that means we try to make it more and more random. Okay, the final value more and more random. But whatever the hashing function we use, there's a possibility of collision. Okay. So then we need collision management techniques. So there are 2 types of collision management techniques we look at in data management subject also. Open hashing or the separate chaining, where we put it into, we'll take one by one. We put it into a linked list. So when this is already occupied, that means there's a collision. We link it to another location and save there. If you have another collision for the same location, we link it to another thing and save it. Like when this is collided in this block, we hash it, link it to another block, another free block. But assumption is it will be very rare. Okay, sometimes no collision will occur to that block, or maybe 1 or 2 additional blocks may be needed, not more than that. So that is one of the collision resolution technique. We call it separate chaining or open hashing. So the second one is open addressing or the close hashing. In that case, either we can put it into the next available location. So when this is collided, we put it into the next available location. Or if it is also there, next available. Or we can go for something like double hashing. When this is collision here, we use another function, hash function, and go there, and maybe it is available. Okay, so forget about the quadratic probing, because it is now not in your syllabus. They will not ask that. Right? So likewise, there are collision management techniques. 2 techniques. One is separate chaining. The other one is you look at the next available location, or you do use another hashing function to find the alternative locations and so on. Okay. And searching is super fast because you use the same hash function. So then you either find it exact location, or you go through the chain if you use the separate chaining, or you use the other technique of looking at the neighboring place and you find the value. If it is not there, you can quickly say not there. If it is there, with 1 or 2 access, you find it. So therefore, this is a data structure. So that is why we use hash map, hash table in Java. So they have used that particular concept to keep the data, especially if you are keeping a lot of data. So it will calculate the hash value, and that hash value will be used for the memory location. So then you straight away go to that memory location and get it internally. But that is not something you do. Your Java will do it. Your Java or your Python or whatever, the language will do it. But internally they use the concept of hashing. But usually it is worth when you have large number of data, thousands and right, sometimes millions of data, you keep it in the memory. Okay, hashing. Because it directly calculates where to go and find the memory location. If it is programming or if it is databases, of course, hash index, it will say exactly this block you have to go and that block you have the data. Rarely that block will be changed to another block or something like that. Okay, that is collision has occurred. Right, any questions? So that's it about hashing, because hashing is now not officially in your data structures and algorithm, but I just again look at it as a data structure. Okay. Right. So now we'll take a break. So today we will not start the binary or the trees. So now we have two data structures and two algorithm topics. The two data structures are trees and graphs. Then the algorithm, we have search and sorting algorithms. Okay. So then syllabus is over. Right. So we'll take a break. After the break, we'll look at data management. So we want to continue with our indexes. Okay. Index concepts. Okay. Right. So now it's 10:35. We'll be starting at 10:50. Right. So this is one of the harder topic, okay, in data management. So therefore, pay a lot of attention to this one. So the next topic is not that difficult. That is distributed databases. Another difficult topic is your final topic, that is concurrency and transaction handling. Okay, so concurrency and transaction handling and database indexing are the two challenging topics. Okay, two challenging topics. Right. So let's move on. So with last time we discussed, oh, actually now we have been discussing databases for database indexing for 2 days, 2 sessions. Right. So we have already discussed about the hardware aspects, how to access storage hierarchy and so on. So that's we have done. Then the structure, different type of files, what is heap file, what is sorted file, right? What is hash file? We have done those things also. That's all are done. And also we look at what is fixed length record, variable length record, what are the pros and cons, what is span, unspan. Okay. And so we have done those things also. And so then we discuss what is a block. A block is the smallest unit that computer can access from the disk, and block factor, number of records in a particular block. Okay. If it is unspanned, you have to floor it because you don't keep a part of a record in a block. So therefore you have to floor it. Okay. So then you can calculate the unused space. If it is unspanned, that is B minus block factor into number of records. Okay. Right. So the number of blocks needed is number of record divided by block factor. Right. So block factor is number of records in a block. And number of blocks needed is number of records divided by block factor. Again, you have to, now we have to ceiling. Okay, now we have to ceiling, because if you need 2.8 block, that means you need 3 block. Right. So we did some calculation last time. So that is what we did last time. Right. So then we moved on to, remember, all the file operations are ultimately, whether you do insert, update, delete, it's read and write operation. But if you do select or retrieve, it's just read operation, right? So that is another thing you have to understand. That we have done those things. Right, so we look at the differences between a heap file, just we add it to the end. And also we discuss what is a sorted file, its advantage. We can do a binary search on the sorted field. So therefore, number of blocks needed is log 2b, okay, number of blocks. And of course, the hash file, hash structure, where you just calculate the hash value and go to that block, and block data is available in that particular block. You don't have to, unless there's a collision. In case of collision, that block will say you have to go to the other block and see. Or if it is double hashing, you have to use the other hash function and go there and get it. Still, it is maybe 2 blocks. Okay. Right. So there we look at in detail about hash. That is why they have taken it out from data structures there. Okay. So we look at the internal hashing and external hashing. In external hashing, we use what is known as bucket. Okay. So we have done those things. Okay. Right. So then we moved on to last time we moved on to indexes. So indexes is where we sort data, either data file or we sort data in an index file and then go to the data file. And we look at, there are 3 types of indexes or indices: primary index, clustering index, and secondary index. So remember, primary or clustering index is related to how we order the data file itself. So that means your data file is also in that order. The index is always a separate file, but if your data file is also sorted in the same order as your index file, then it is either primary index or clustering index. Okay. But if you have your data file ordered in a different order and your index file is in another order, so then it is a secondary index. So now you must know these things. And if you have any questions, you need to ask and get it clarified. Okay. So index means always a separate file. Okay. Index is always separate file. Right. So then last time we look at only primary index. So today we want to look at the secondary index and clustering index and secondary index. Okay. So what is primary index? So you have your data file. Usually data files are ordered in primary key. Let's say student ID. So then we have an index file which has the student ID and block number. Right. So maybe set of student IDs are in first block, another set of students are in second block, another set of students are in third block, and so on. So remember, primary index is a sparse index, not a dense index, because if you have 1,000 records in say 5 blocks, your index file has only 5 records. So that is super important, right? So I explained you that because we are keeping only the value of the first record of the first block, first record of the second block, and so on. So therefore, you have to go to the correct block. Then you do a search, because you can take the entire thing into the memory. Do a search in the memory is fast. So then you have to locate your record in the index file, primary index file. So then using the block pointer, you have to go and get the related block unless there's a collision. So that's it. Okay. So that is what primary index is. Right. So your data is physically ordered in the same order as your index file, but your index file is very small because it has less width, because you have just one field and a block pointer, and it has less record also because one record per block typically. Okay. So first you do the search in the index file, and then you do the search. Go and not search, then you go and get the block. Okay. Right. So any questions on that? And we did a calculation also. Okay. We did a calculation also. So the primary index file has a primary key field of the first record of the block only, and the pointer to that block. Okay, only first records. Okay, so therefore you have very little number of entries in the primary index file. So this length is smaller, width is small. Length is very small. Okay. Right. So if one block is not enough, so then they can chain it to another block, extra block and so on. So then of course, then you have to access that block also, but those are special cases. Usually the exam question is for a happy scenario, general case, not special case. Okay. Right. Remember the primary index are sparse index. Okay. Sparse index. So because you can do binary search in your index file, it is log2b, where b is the number of blocks in your index file, and then +1. That is, you go and get the access the data block. Okay. So therefore, it is log2b +1. Okay. Log2b +1. That additional one is your actual file. Okay. So this b is number of blocks for the index file. Okay. So that is most of the time that number of block is also 1. Okay. Because you have only one entry per block. Okay. Right. So that is where we stopped. Okay. That is where we stopped. And remember, we can have only one primary index because it must be your ordered, sorted field. Usually that is primary key. Right. So now we move on to the clustering index. Nice. Clustering index. So remember, you can have either primary index or clustering index. You can't have both because both are ordered in the same order as your physical file. So if your physical file is ordered according to the primary key field, and of course your index file is also, then you have to order according to the primary key field, then it's a primary index. But there can be a situation where your physical file is not ordered or sorted according to the primary key, rather different value, maybe a foreign key. Say this is employee details. So if it is primary index, here it is employee number. So some set of employees are in block 1, some set of employees are in block 2, and so on. So then for each first entry is in the index file, and you have the index primary index. Let's assume your data file is not sorted according to the, say, employee ID, rather department ID. So department ID is a foreign key maybe. So now department 1 employees are there, then department 2 employees, 3 employees. That is how you have physically stored it. So then you can go for a clustering index. So obviously you can see that if it is physically ordered according to department ID, it is not physically ordered according to the employee ID. So therefore, when you go for clustering index, you can't have primary index because this file cannot be sorted by two different fields. It can be sorted by only one field. Okay, right. So that is what clustering index is. So you have sorted it according to different field, and therefore your index file is also sorted according to that field, which is not the primary key, maybe department ID in your employee table. Okay, right. So that is what clustering index is, and we can have only one of the either clustering index or primary index. Even clustering index, you can have only one clustering index because you can sort it according to only one non-key field. Okay. Right. Again, your clustering index file has only two entries, that is clustering index field and the block pointer. Right. Index field, block pointer. But now we have a small issue where the primary key is unique. Right. Primary key is always unique. One record for one value. But when it comes to clustering index, because it's a non-key field, it can be still unique because your non-key field can also be a unique field. like maybe not employee ID, rather NIC. Or it can be a non-unique field like department ID. Then obviously there are multiple records of the same department. So therefore, when it comes to clustering index, there are two possibilities. One is still your clustering field is unique. Then it will be pretty much like the primary index. It will behave pretty much like a primary index. But there is a possibility that your clustering index field is not unique, like department ID. Okay. So if it is not unique, there's a difference how you manage it. Okay. Right. For example, say assume that our clustering field is department ID, and this is employee file. Okay, employee file. Now you have clustering field is department, so therefore it's a department 1, 2, 3, 4, 5, 6, 7, and so on. So there are two approaches in this kind of situation where your clustering field is not unique now. One approach is you take the first record of each block. Sorry, for each department ID, you have entry. Sorry for that. Okay. Say I have 8 departments. So then this is approach 1. For each department, I have a block entry in my clustering index file. Say department 1 is in block number 1. So therefore, it will point to the block number 1. Say department 2's first record is in the block number 1. So then that is also taken to the block number 1. But maybe the rest of the department 2 are here. That is fine because we connect this block to this block. So if you are looking for department 2, you will be directed to the block 1. Then you will find your record, though if it is not there, they will say, okay, now you have to look at the next block. Because there can be department 2's records there. Then you have to access this block and then this block also because it is not found here. Okay. But you don't have to go to the next block because 2's are over. So then department 3, its first record is in this block. Of course, some records are there, but what you have is the first block of that particular department ID. Okay. So that is one approach. So then if you have 10 departments, you have 10 records here. 10 entries here. That has only the clustering field and the block pointer, but there's a possibility of you have to access additional blocks. That possibility is there. So that is approach 1. Approach 2 is, so this is entry per clustering index field value. If you have 10 departments, you have 10 record here, 10 entries. Okay. So approach 2 is, right. So you have 1 entry per each block. So that means if you have 5 blocks, you have 5 entries. Earlier, if you have 3 departments, 3 entries, maybe 5 blocks. But this time, if you have 5 blocks, you have 5 entries. Okay, and it's always the first entry of that block, right? For example, this is the first entry of this block. And second one is first entry of this block. And this third one is first entry of this block. And so on. The reason is when you have a different department ID, I made a small mistake here. So now what? Sorry, I made a small mistake. So the idea is, say department 1 records are here in the first block. Now, even though my block is having space, we don't put the department 2 into the same block. We always take a new block. Okay, new block. So then department 2 are in the second block. We don't keep department 3 in the same block. So for department 3, we go for a different block. Okay, different block. So that is that approach. But in that approach also, maybe a particular block key is not enough for a particular department because there can be so many employees of that department. In that case, we have to change it to another block. But again, in that block also, we don't keep a particular other department. For example, if you have all department 3 employees here and it is filled, it is changed to another block. And there also, you have only department 3 employees. You don't put department 4 employees and so on. Okay, and so on. So that is another approach. And again, you will find that if you have 10 departments, you have 10 entries. Earlier also, if it is 10 departments, you have 10 entries. But this time the difference is you don't mix employees in a particular block. So therefore, this is sort of a waste of your storage. But at the same time, if you are growing, right? So there's always extra space. You don't have to chain it much because already you have a well-defined blocks, dedicated blocks for one. Extra blocks are also dedicated for one department. So therefore, this approach is little bit more easy to manage, but it will take little bit more storage also because we don't mix, right? We don't mix. But in both the cases, the number of entries in the clustering index file is same as number of distinct values in the for that particular field. For example, if it is department ID, if you have 10 departments, you have only 10 entries. So there you can do a linear search because it's sorted according to that. Then you have to do additional access or maybe two or three access because it might be changed to another block. Okay. But unless they have mentioned about that kind of a collision, you can always assume that just one more access and you are done. Happy scenario. Right. So that is how clustering index work. Clustering index work. Especially if it is not a unique field. Not a unique field. Okay. Because not a unique field, now you have two approaches. Approach 1 or approach 2. Okay. Right. So now let's do a calculation. Right. So because in the exams, what you get is not theory. Usually what they ask is calculations. Okay. Right. So let's do this question. For the same ordered file that we discussed last time also. So that means it has 300,000 records and block size is 4096. Block size is something to do with the disk, right? Not something to do with the file. So each block can have 4096 bytes and we have 300,000 records, maybe employee records. Let's say we have used zip code, which is a non-key field. Now our clustering index field is zip code. Okay, zip code. Maybe the country has 200 zip codes. Okay. Assumption, each zip code has equal number of records. Now, let's assume that each zip code has roughly equal number of records. That means employees are coming from randomized manner. Okay. And there are 1,000 distinct values for zip codes. There are 1,000 zip codes, 300,000 employees records, but they are coming from 1,000 different zip codes. So that means if you go for a clustering index by zip code, so that means our index file must have 1,000 entries. Whether we go to approach A or approach B, that doesn't change. Okay, that doesn't change. Right. Right. And they say index entries consist of 6 bytes for the zip code. Remember, the index file has zip code and block pointer for the data file, which is sorted according to the zip code now. This is now sorted according to zip code. Okay. This is also sorted according to zip code, but this has only one entry per one zip code. So therefore, this has only 1,000 entries. Okay. This has 300,000 entries. And both are sorted according to zip code now. Okay. Right. So 5 byte for zip code and 6 byte for block pointer. So therefore, this record is 5 plus 6 that is 11 byte. 11 byte. Okay, 11 byte. 11 byte each. Right. So now we can calculate the size of the record is 11 byte. So now you can calculate the block factor. Right, block factor, that is how many records per block. So our block size they have given as 4096. Sorry, not number of blocks, number of records per block. Sorry, number of records per block. So that is one block size is 4096 divided by one record take 11 bytes. So therefore 4096 divided by 11, you have 372 index entries per block. And 372 index entries can be added to one block. Now remember, we have 1000 index entries because there are 1000 zip codes. So therefore, how many blocks are needed? Number of records divided by block factor. That is 1000 divided by 372. Of course, here you have to floor it, right? Because if you need, if you can keep 12.8 entry, we just have to take it as 12 entry. So that is therefore we have to floor it. But number of blocks we have ceiling. Remember, number of blocks is number of records divided by block factor. Number of records is 1000 because there are 1000 zip codes, different zip codes, and each block can have 372 entries. So therefore 1000 divided by 372, we have to ceiling it, because if you need 2.1 block, that means 3 block. So therefore we get 3 blocks. So that means our index file need 3 blocks. Right? Index file need 3 blocks. And remember, we can do a binary search. Now we are searching by zip code. We search by zip code. Okay. So therefore, we just have to do a binary search. In binary search, it is log 2 because every time we take half out. Now remember, I discussed that the big O notation binary search is O log 2 and that is same, because every time we take half of the stuff out because it is in the other half, because it's sorted. Therefore, now how many block access needed? For worst case, in the binary index file, log 2 number of blocks is 3 because we take block by block. Log 2 3 is you have the ceiling, which is 2. Which is 2 because next one is 4. 4 is 2 to the power 2. Right? 4 is 2 to the power 2. So 4 is the next bigger value. 4 is 2 to the power 2. So 2 is your value. So therefore, now you know that how many access we have to do? 2 block access maximum. Then you get that block entry, that zip entry, and zip entry has the block number. So then you have to have an additional 1 block happy scenario. Assume that it is not changed. So therefore, we have to do another access following the block pointer. So that means 2 plus 1. You have to do a 3 accesses. So 2 block accesses to get the block number. Then you have to do additional access, that is 3. Right? 3. So therefore, the final answer is actually not 2. I don't know why they have not given it. Maybe later. No. No, right? They haven't given. So the final answer must be actually not 2. 2 plus 1, 3. Okay. So maybe for some reason they have not given it. So this is block access for binary search. So then we have to have another, because now you got the data block ID. So then you have to go and get that block. And sometimes we have to get another block, but we'll look at only the happy scenario. So therefore, number of block access needed is 2 plus 1, which is 3. Okay, 2 plus 1, which is 3. Right. So that must be the answer. So any questions? So that is clustering index, assuming we have clustering index. Okay. Of course, if you have a clustering index, you don't have a primary index, because That is how it works. Okay. Right. So now we move on to the secondary index. Secondary index. So remember, you can have any number of secondary indexes. You can have only a primary index or one clustering index. One primary index or one clustering index. But while you are having a primary index or clustering index, you can have any number of secondary index, because secondary index, we don't assume that your data file is sorted in the same order. No, we don't assume that. So in secondary index, your data file is maybe sorted in the primary key. Your index is something else. Maybe your data is sorted in employee ID, but your file is index file may be sorted according to maybe the designation. Okay, so or salary. Okay, so that is, then you can have another secondary index. Maybe this is sorted by designation, this is sorted by salary, another secondary index which is sorted by another thing, and so on. You can have any number of secondary indexes. Okay, and again, that secondary index can be unique field, or secondary index is not a unique field. If it is salary, it is not a unique field. But if it is again email address or something, it is also unique field. Secondary index is also unique field. Okay. Now the only thing is you have to think a lot of things, right? Possibilities, what are the possible things, what are the impossible things, right? And so on. And also do the calculations. Okay. So therefore, secondary index is an additional medium for accessing the data file. When already has a primary access, that is primary key index or clustering index. Okay. Right. So you can have few secondary indexes, not just one, maybe 2, 3, 4 secondary indexes. Okay. So if the index is secondary index is created for a candidate key, it's a unique field, secondary index. But if not, it can be even non-unique secondary index. Okay. Right. So remember, our primary index and clustering index both are sparse indexes, not dense index. So maybe you have 300,000 records, but in the data file, but my index file may be having only 1,000 records. Okay. Sorry, not primary index. I made a mistake. Your clustering index is clustering index can be sparse index, right? That is what we did last time. For example, my data file has 300 records, but my index file has maybe 300 records. There are 300,000 here, 300, because there are only 300 zip codes. Okay. But if it is a primary index, when my data file has 300,000 records, my index file also has 300,000 records. Remember? Because primary key is unique. No, sorry, not that. Sorry, not sorry. Primary index is also sparse index, because you can just keep the first record in that block. Sorry for that. Okay. Remember, we just keep the first record of the block. So therefore, primary index is also sparse index. Secondary index also, it can be a sparse index. Okay, it can be a sparse index. Because sorry, the clustering index can also be sparse index, because we are just keeping one entry per one value. One entry per one value. So that is if it is not unique. Of course, if it is unique, that is a different story. Right? Then it is a different story. But when it comes to secondary indexes, now it must be dense index, because your secondary index is not the field that your data is physically ordered. So therefore, there's no order. So therefore, if your secondary index has 1,000 entries, you have to have 1,000 records or 1,000 values. Okay. Because there's nothing called anchor record. There's nothing called we can only keep track of the first record. No, because our field is a different field than the data file. Okay, so therefore first record entry cannot work for secondary indexes. Okay, secondary indexes. So that is something we have to understand very clearly. And secondary indexes are super important because then when we are searching for something in secondary index, because physically it is not sorted in that order, we can do a binary search in the secondary index file, and then we can go and get the record from your data file. Okay, so disadvantage is your secondary index file has a lot of records, but still it is a small file because it has only the secondary index field and the block pointer. Right. So therefore, it's faster because you can do a binary search. Otherwise, you have to go to the data file and do a linear search because it is not sorted there. So rather than going to the data file and do a linear search, doing a binary search in the secondary index file is faster, though your secondary index file also has a lot of records. Though it has a lot of records, its width is small, and also you are doing a binary search. So both contribute to less time. Okay. So therefore, we can see secondary indexes are more important because we have to do a linear search of the data file if secondary index is not there. Right? Remember, linear search is very costly. Okay. But binary search is faster. And also our file size is also smaller. So then we have to do just one subsequent block access. Right. So let's do a calculation. Okay. So this is without index calculation. Right. So then next page we have with index calculation. Right. With secondary index. This is without index. So don't think that this is actually this is without index. Okay. So they have just mistyped it. Right. So now let's do the calculation. Okay. So this is the question. I read the question. If we take the same example in primary index, that previous example, and assume we search for non-ordering key field, which is 9 byte, right? Which is 9 byte. So that means something like this. So this is my index file. It is 9 byte. 9 byte. That is non-ordering key field. In a file with 300,000 records. So your data file has 300,000 records. 300,000 records with a fixed length of 100 bytes. So your data file has fixed length of 100 bytes for each record. And given the block size, so the block size is also given 4096 bytes. Okay. And now you can calculate the block factor. That is, one block is 4096 and each record is 100 bytes. So this is block factor for the data file. Okay. So block factor means number of records in a block. So block factor for the data file is 4096 divided by 100 because one block can have 4096 bytes. Each record is 100 bytes. So 4096 divided by 100, you have to floor it, right? Because this is number of records per block. If it is 40.8, we have to take it as 40 records because we always assume unspanned. And there you will get, there are 40 records per block when you floor it, okay? That means one block can have 40 records. Next block, another 40 record. Okay. Now you can calculate number of blocks needed for the data file. So still we are not assuming index. Okay. We are not assuming index, right? So we are only talking about the data file. So now we know that one block can have 40 records. So therefore now when we can calculate how many blocks are needed. How many blocks are needed? 300,000 divided by 40. Right? 300,000 divided by 40. Now we have ceiling, because if you get something like 80.8, that means you need 81 blocks. Right? You have ceiling. So there you will get 300,000 divided by 40. Ceiling, you will get 7,500 blocks. Now we are only concentrating on the data file. Okay. Right. So that means we have 7,500 blocks. And this is the data is saved not by our field. It is maybe sorted by primary key. Right. So maybe we are searching it by something like email address. Right. Email address. So now there is no index. Right. Of course, the primary index is there, but we can't use primary index because maybe the primary index is for the employee ID, but we are searching it for employee, maybe employee email address. So therefore, we can't use the primary index or the cluster index. Right. And assume that we don't have secondary index. Now we have no other option but go and take one block at a time and do a linear search. So you take the first block and see whether that email address record is there. Take the other block, see whether that email address is there in a record and do it. So therefore, we have to do what? Linear search, taking one by one block by one block. So therefore, how many blocks we have? 7,500. So therefore, worst case, that is you found it in the last block or it is not found, you have to access 7,500 blocks. That is worst case, because we have no other option but linearly take block by block, because we don't have an index yet, or the index is there, which is primary index or the clustering index, but it is not related to our field that we are interested. So therefore, worst case, 7,500 block. Average case, 7,500 divided by 2, 3,750, which is lot of disk accesses. 7,000, so 3,750 block we have to access one by one. It is not there, then you go to the next one. So that is average. Worst case, you have to access 7,500. Maybe your data is in the last block, or now only you say it is not there. Right? So that is if you don't have a secondary index. Right? If you don't have a secondary index, maybe you have a primary index or clustering index, but we can't use it because it is what we are searching is different field. Okay. Right. So why we do this calculation? To take it as a reference, how inefficient is. It's even average case, you have to access 3,750 blocks. Now let's see what happens if you have secondary index on that field. On that field which has 9 byte length. Okay. Right. So now we have the secondary index. Okay. Let's assume we have secondary index now. So now secondary index file has secondary index field, which is 9 byte. They have mentioned that it is 9 byte width. Right. 9 byte, non-ordering key field. And they say block pointer is 6 byte. Right. Block pointer is 6 byte. So therefore, this is 9 byte. 9 byte and block pointer is 6 byte. Okay. So therefore, this length is one record is 15 byte. 15 byte. Now, remember, we need to have one record per block. So we have 4,096 block size. So therefore, what is the block factor? 4096 divided by 15. That means how many records fit into a one block in the index file. In the index file, 273 records fit into one block. So that means we can have 273 index records in a one block. One block. 273. In another block, another 273 and so on. Okay. So that is for the secondary index. Now remember, this is a non-order field, maybe email address. So therefore, for each entry, we need an entry here. For each email or each record, you need an entry here. So that means how many records are there? 300,000. So therefore, here we have index file also, we need 300,000 records. Right? Because your data file is not ordered according to this index field. So therefore, there's no other way. So each record, each email address, you must know what is the block. If you have 300,000 record, here also 300,000. But the good news is, this is now sorted according to the, say, email address. But still, you need the same number of records. So therefore, how many blocks are needed? So you can have 273 records in one block. We have 300,000 records. So therefore, how many blocks needed? 300,000 divided by 273. Right? We have to ceiling. Why? If you get 8.5 block, you have to say 9 block. So now you can see that you need 1099 blocks. 1099 blocks needed. Right? So earlier we calculate how many blocks needed in the data file. How many blocks we needed for the data file? 7,500 blocks. Right? So data file we needed 7,500 blocks because record size is bigger. Here we have 1099 blocks. Right? 1099 blocks. But there's advantage. What is that advantage? Here we can do a linear search, binary search, because now this is sorted by that field, secondary index field. So therefore, though we have 1099 blocks, we can do a binary search. So therefore, the worst case also, number of access need is log 2099. Then you get that entry. Then using that entry, you have the block number of the data file. So then you have to have another additional one access. So that is, you go and get the record in that block because that block has the record. So therefore, number of access block access need is log 2099. You have to ceiling plus 1. So 1099 is the next 2 to the power is say 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. 2048 is 11, right? 2 to the power 11. So therefore, it is 2 to the power 11. That means 11 access because it's a binary search can be done because it's sorted at 11 access. But now we have to do one more access because now we got the block number of the data file. So 11x plus 1, that is 12. So how do you get 11? Because the next value in 2 to the power value is 2048, which is 11. That is 2 to the power 11. So therefore you get 11 and you need one more access because now you have the block pointer of the data file. You go there and get that block, and that block definitely you have your record. That email address or whatever. So therefore, now how many blocks we need? Worst case, 12 block access. After using the secondary index, we need 12 block access. But without secondary index, how many blocks we needed access? Without that, average also 3,750. So what kind of improvement is that? Without secondary index, because we had to do the linear search, we have to do 3,750 block access on average. But with secondary index, we have to do only 11 block, worst case 12 block access. So 12 is far better than average case of 3,750, or the worst case of 7,500 block access. So that is why we say secondary indexes are super important if you are frequently doing search on that particular field. Okay. Right. So that is what secondary index is. So the other advantage is you can have any number of secondary index files, maybe one secondary index file for email address, another secondary index file for salary, and so on. Right. And so on. But again, there's a small issue if it is a non-key field. So email address unique, but salary is not unique. Okay. So that is another issue we have when it comes to secondary indexes, because same salary can be mapped to multiple records. So, but that is not our problem. If you are searching by salary, what we can say is all these employees are having that salary, because when you give non-unique field, we can't give you one record. So then we can say, okay, these 100 records are related to that salary. Right, related to that salary. Okay, but again, it is not very efficient, because now these 100 records may be in 100 different blocks, because your data file is not sorted according to the salary. So therefore, this approach is not that good for that kind of a scenario where you have multiple data. So the same value is there. Okay, so you can see the pros and cons of each and every approach. Right, each and every approach. So maybe it is good for this kind of scenario where you have unique entry, but not good for duplicate entries. Okay. So just think about those things. That is why I told you this is the hardest topic. This is the hardest topic. And that is why this was in the final year. And I know that when this subject was in the final year, some years no one has passed database. No one. So even the best student come and say, I failed database. Right? So then after 1 month, they come and say, I have passed database. So that means the UCSC has added some marks, because there are no enough students for the convocation. So then they add maybe 20 marks each, and all of a sudden those D minuses, Ds have become Cs, and they go for the. So that is the challenge they used to give when the subject was in the final year. But now they have taken it to the second level. So therefore, be prepared. Okay, be prepared. So these are not easy. So you may feel like it's easy, but when you go to the exams with the exam pressure and so on, so you can really mess up the questions. Okay, right. Even not you, even an experienced person who know the theory, sometimes we get confused, right, with the wordings and so on. Okay, right. So that is secondary index level calculation. Okay, so you have to keep track of a lot of details, pay a lot of attention to details when you are doing the calculations. Okay, right. So basically you can see that this is a lot of improvement, right? Accessing something like 12 blocks is far superior than accessing something like 3,750, which is the average case for not having secondary index. Okay. Right. So remember, your physical or primary or clustering index gives you the physical ordering, or it is compatible with physical ordering, whereas your secondary index gives you a logical ordering, because your index file is in one order, which is the index field, but your data file is in a different order. So that is why you need to have the same number of records in the index file. Your data file has 300,000 records. Your index file also has 300,000 records. So then why is it still faster? Two reasons. One, you can do binary search. Second, your record size is smaller. Right? Record size is smaller because we have one record, the index field plus blocks width. Okay, so therefore still it is fast because of the possibility of binary search. Right, so next we have the multi-level indexes. Okay, multi-level indexes. So multi-level index means you have index file. Now this is the toughest one. So you have to look at one index file, then that go direct you to another index file or set of index files. So then maybe that index file tell you where to go, direct you to the data file. Or maybe that is also directing to another index file. And that index files give you the actual block number. So that is called multi-level index. So why do we go for multi-level index when you have very large number of entries in the index file? Right? Very large number of entries in the index file. For example, now previous example also we got that our index file has 300,000 records. So therefore we needed a large number of blocks for the index also. Right? Large number of blocks, even 1099 blocks for the index file itself. So in that kind of a situation, rather than going for one index file, we can make it to a multi-level index file, and we can improve little bit at least. Now remember this, with single level index we needed 12 blocks, but if you make it to a 2-level index, sometimes we can do this with maybe 8 block or 6 block. So that is sort of a improving the performance by another 50%. So in order to do that, we have to go for multi-level indexes. Okay, so that we'll look at next time, and then we can finish it. Okay, we can finish it. Right. So we'll stop at this point. So just pay a lot of attention to those questions. Okay. Before coming to the next session, because we will finish it. So this is the hardest topic. Right. So what we are doing is the hardest topic in database, because the next topic, though it is hard, you can understand it, the transaction management, and of course the distributed database is super easy. So try to pay a lot of attention to this topic. Okay, right, we stop at this point.